Okay, so we have number 39 on the review. We have a commutative ring R, and we have for every element A and R, AR equals R. And when we were doing this in class, I didn't realize, or I wasn't remembering that this was for every element in A and R. This does make it a little bit, makes it a lot easier actually. So the basic start is fine. So you fix some A that's not equal to 0. We should put that there too. That's part of this condition here. All right, so we're picking some A and we're fixing that A, and like we did in class, of course, A times 0 is 0, but then we can list out all the ring elements all the way down to A, R, N. And what happens is we will get back every one of the ring elements will show up here also. That's what this part is telling us, that AR equals R. It tells us that we're going to reproduce R here, and that with no duplicates. If we had any duplicates by pigeonhole, we'd be too small here. So where do we go from here? Well, first of all, we want to identify a unity. And since one of these elements here is A, we're going to say that somewhere in there, since A shows up on the right side of these equations, there's got to be an R that we multiply by A to get back itself. So this is going to be our candidate for unity. But just because we showed that when you take it times A and get back A itself, that doesn't mean that RK is the unity itself. Remember, for example, in the group Z10, in the ring Z10, the element 6 times 6 gives you 6. 6 times 4 gives you 4. 6 almost functions like the unity in Z10, but it's not the unity. 1 is the unity in Z10. So just because we show that this is functioning so far as the unity doesn't mean it is in general. In general, we have to show that for an arbitrary x, this would happen. So let's say let x be a member of the ring, not equal to 0. Let's just work with the non-zero here. So x has to show up somewhere over here, which means that there exists some L such that A R L equals x. All we're saying there is x is showing up somewhere here. This arbitrary x that we've chosen in the ring has to show up here somewhere. So we have A R sub L x equals x. Okay, and just to be clear, we don't know this is true yet. This is our goal here. If we can get this, then we know for sure that RK is the unity. Okay, so we have this A R sub L equals x. Let's multiply both sides on the right by RK. X times RK. Okay, and now because we have the fact that R is commutative, we can rearrange these things here a little better. So we could say that A RK times RL equals x to the RK. And then A RK, we should that up here, that's already A. So A RL equals x to the RK. But A R sub L just equals x. So we have x equals x RK. So since x was arbitrary and it's multiplied by this candidate and we get x back itself, now we know that this is the unity. Okay, so we have the unity. Once we have that, it's actually fairly straightforward since we have this situation happening for every element in the ring. So if we take an arbitrary element, let's just say y be an element of the ring. We could do a similar thing like we did with the a's here, and y times r1, y times r2, y times r3. And every non-zero element is going to show up here sooner or later. So then there will exist some rm such that y times rm equals rk. So in other words, rk is going to show up here on the right somewhere, and that is the unity. So since that's the unity, we'll have this as the inverse of y, and since y was arbitrary, so y inverse exists, and R is a field. It's now a commutative. It's a commutative ring with unity where every element has an inverse, so that's the definition of a